Hello, dear friends. Today I'd like to talk to you about something very, very important. The dice of life. What is this dice of life? Now, first let me start introducing some friends to you. This friend is called alanine. Right? Alanine is an amino acid. Now, there is going to be a lot of science on this lecture, but don't worry, everything is going to be explained. So you're going to enjoy it. And I'd like to show you some things that perhaps you didn't know, which is going to be interesting and enriching of your life, I believe. Now, alanine is amino acid and is responsible for a lot of things in our body, like immunity, the synthesis of proteins in your body. Actually, almost all proteins of your body, in my body, have alanine. Also, alanine is responsible for feeding your brain with energy. Of course, for those people that use their brain, the people that don't use their brain, this is not concerned, but I believe that you're not one of them because you're watching this movie. So I believe that that's the case. 20 different amino acids build one protein, just one protein. 20 different amino acids comprise all the building blocks of the proteins of your body. And they can combine. They combine very interestingly to build proteins. And everything in your body is proteins. Even your bones are proteins. Your brains are proteins. Your hair is a protein. Your nails are protein. Everything in your body is consisted of proteins. So the proteins, this is why in Greek, protos means first. So it's very important. This is why they call it protein first. It's important. This is why we're going to talk about the dice of life. Now, how can life be connected with dice? This is what we're going to learn in this lecture. So, the amino acids are 20, but we need 100 and more than 100 to combine to get one protein. And your body has different proteins in your body. A lot of protein. Only structural proteins, the proteins that make your structure are more than 100. Now we've got much different variety of proteins, which are always made up of these amino acids. And one protein, remember, takes more than 100 amino acids. Now, the amino acids connect to each other, and they create, two are connected with each other, these amino acids. They create so-called peptide. And it's called dipeptide because we've got 2 amino acids. 3, it's called tripeptides and polypeptides of many amino acids, which is also the polypeptides are the proteins. The reaction that takes place of combining this is it's very complex. Just to simplify it, is that this way. Now you're taking sugar. This is the formula of sugar. When the sugar is burnt in your body, it's converted down to simple water and simple carbon dioxide. The carbon dioxide is exhaled. So you're exhaling it and you've got energy. So this process of converting sugar to carbon dioxide and water releases energy. This energy, right, is used to take the building force of your energy, adenosine diphosphate, and converts it to adenosine triphosphate. Now, there is a guys that use creatine, and it's very popular because it's very cheap. What the creatine is doing is taking one phosphate ion, attaching it to diphosphate, and becomes triphosphate. Same thing is doing the sugars. This is why they say take creatine with sugar, or with glucose, or with honey, with anything sweet, with something that can be converted to energy quickly. So you take sugar or any carbohydrates, it's converted to energy. The energy is used to convert the main building block of your energy, adenosine diphosphate, turns it to adenosine triphosphate. Now, I want to think about two weights of one pulley. One is pushing down, that means it's heavier, the other one goes up. So the sugar, when it's converted to energy, pushes adenosine triphosphate. Now you've got energy in your muscles. Adenosine triphosphate stored in your muscles. Now you can run, you can walk, you can do everything. This adenosine triphosphate, all right, this amino acid that we're talking about, this is not a spontaneous process, right? It's not a spontaneous process to combine amino acids. So if you take a lot of amino acids, you pile them together, hundreds of them, and you mix them and you try to make it, it's not going to happen because the process is not spontaneous. Now, we need to help it. And as we help adenosine diphosphate turn to adenosine triphosphate with this pulley, one is heavy, another one is lighter. In this way, again, now we're going to help the amino acids, give them energy to turn into proteins. That's not going to happen. Just think about it. We need sugars. Sugars release energy to adenosine diphosphate, makes it adenosine triphosphate. The pulley is pushing up, the other one is here. This is taking the energy and combines the amino acids to turn your amino acids to proteins. Now, if this is not happening in your body, right, you're going to starve and you're going to die. And if your body are not regenerating your proteins, they are regenerating from 1 day to 10 years, depending what kind of proteins, we're going to talk about it. You're going to die. You're finished. All right. So now, this is how the amino acids are combined. On top of that, because the amino acids, they combine, right? They combine in a chains. Now, it's called condensation reaction because one of the ends of the amino groups of the amino acids combining with another group with the other end of the other amino acids, creating the peptide bond, and this peptide bond, it's actually connecting them. But this we need energy. Without energy, it's not going to happen. And this energy, as I explained, comes from sugar. Sugar comes to adenosine diphosphate, to adenosine triphosphate. And now this energy of adenosine triphosphate is pushing the amino acids and creating and converting them to proteins.
So here's the molecule, and you can see the triphosphate ions at the end, on the right side. And when the last phosphate ion is released, it releases also, disattached, it's releasing also energy in the presence of water. So the process is very simple. In the presence of water, adenosine triphosphate turning to adenosine diphosphate with the phosphate ion and energy.
Something very interesting about the proteins in your body that you didn't know. They're consistently the same mass proportions. The miracle element in your body and the miracle element in your, in the whole nature is carbon. Carbon get 4 valence electrons. That means he can connect to another 4 or less or so and so. So it makes it very flexible. The connection that makes it with the bonds that it makes with the other elements incredible. Just to give you an example, the carbon that got carbon are more than 30 million. More than 30 million. While all other that doesn't connect with carbon are less than 100,000. Now, think about it. Carbon is such a versatile element that the substances that has carbon are more than 30 million, and they are discovered more and more every day. While the other elements that doesn't have carbon are less than 100,000. So one is organic, another one is inorganic chemistry. So the organic chemistry, as you can see, it's much operates with much more substances than the inorganic chemistry. This miracle element, which God created, is so amazing that He can connect in such a way that can create a vast, huge molecules. This can be very functional in our body, that can do a lot of things in our body. That's 53% of the weight of the protein. And I said all the proteins in your body are consistently, remarkably equal with these proportions. 53% carbon, 23% oxygen, 16% nitrogen, 7% hydrogen, and 1% sulfur. So you've got carbogen, which is graphite or coals. You've got oxygen from the air, and nitrogen from the air, and hydrogen from the water maybe, and sulfur. So you take all of these 5 elements and you mix them. You can mix them for billions and trillions and as many years as you want. Nothing is going to happen. Nothing. So how do you combine? How did this combine these elements so that we can have amino acids? The complex reaction is such a complex and incredible reaction that the chance that to happen is huge. But it happens. These elements are combining and your body functions based on carbon. That's what it is. The carbon is not such a big molecule, big atom. It's not also such a small atom. It's not bigger, like little bit bigger than silicium. So the connections are different. And these connections between the carbon atoms make it possible to make a lot of chains. And this chain build a lot of things. So this is how incredible the proportions of proteins are. Now, in your body there is a structure like a muscle, skin, bones, and different other stuff that makes your structure. Vascular system and so much. Now, can you imagine what protein is the most important in this structure of proteins? We said 100 different proteins are discovered as a structure of proteins. Collagen. Collagen takes 6% of your total body mass and is also 30% of your bone tissue. And comprises a lot of things in your body. Tendons, bones, cartilage, skin, and muscle. So now, collagen is extremely strong. His highly organized structure, look at it, that's his structure. His highly organized and very compact structure makes it stronger than a steel. So that means if we had one rope made of steel and one rope made of collagen, the collagen is going to be much stronger than the steel. Right. So this is one of the proteins. Only one of the proteins that's made of 2 amino acids, glycine and proline. Now, if I may ask you, what is the biggest organ in your body? Think about it. Is it the lungs? Is it the liver? The small intestine? What it is? No, it's the skin. The skin is made mostly of 2 proteins, elastin and collagen. Now, can you imagine if there wasn't elastin? You can punch your skin and let it go. And you can see it's returning. If there was not elastin, when you punch it, it will stay there like a plastic. And you have to push it down. So, because it's not so nice your skin to stay like this, right? You can scare the children. So, elastin is working together with collagen so that your skin is very flexible. Your skin needs to be flexible so that you can operate. Every doctor will tell you that there is a different need of needles when they're going to put you an injection. One is if you have to go through the skin, and another one is if it's going to go into the organ, say for example, under the skin. It's not going to go to the skin. It's different. The needle that have to go to the skin it's much stronger, and it's quite different and much different and stronger than the other one that goes for the insides. Now, the protein molecule, as you can imagine, it's quite big. And this big molecule, it's such a wonderful and flexible molecule. At the same moment, it's stable molecule, but it's not so stable so that it can adjust. And at the same moment, it's not so adjustable that it cannot be stable. You understand, there is quite a balance between the stability of this molecule and the flexibility. Now, if it wasn't flexible, your DNA, every day that recreates your body, couldn't recreate it, you will die. But if it wasn't stable, you wouldn't get the same protein, it will disintegrate. So it must be balanced between the stability of the molecule of the proteins and the flexibility. And that's very important to realize. Now, as I said, it's quite a huge molecule. Let me give you an example. How do you weigh a molecule? It's such a small thing. You can't take it and put it on the scale and weigh it and check out how much it is. So how it is? It takes ages for the scientists to discover a way to weigh a molecule. Can you imagine? A simple molecule. Now, the scientists measure the weights, the weight of a molecule, of atoms and electrons and a lot of other stuff, usually in moles. What is a mole? Mole is a unitless number, which is 6.02 by 10 with 23 zeros. So that kind of units you need to have of molecules, 6 by 10 with 23 zeros on the 23rd power, so that you can have 1 mole. Just to tell you, 6 by 10 on the 23rd power of molecules of water, right, weighs only 18 grams. Right. The hydrogen weighs 1 gram per mole, and we've got 2 hydrogens, and we've got 1 oxygen, which weighs 16 grams per mole oxygen. So you've got 18 grams of 1 mole of water. That is maybe 2 spoons of water. That's so much molecules you've got in 2 spoons of water. Now guess how many is the molar weight of a protein. Now, it varies from 5 kilograms, not grams, 5 kilograms to 10 tons. Such a huge molecule. Can you imagine? That is, now think about it, that's not one protein, that's 6.02 by 10 on the 23rd power. That's how much it is. The weight of 1 mole of protein. It's a huge molecule. So that's the collagen, and that's how the proteins operate. Also, the collagen is responsible for the flexibility, together with the elastin again, of your blood vessels. Now, could you imagine what could happen if your blood vessels lose the elasticity? That happens and you get a stroke and you die. Or you get ischemic heart attack and you die. Finish. If they are not elastic. So God created them to be elastic, but we eat meat, we eat dairy, and when you eat the animal puts his fat inside of your arteries. They get clogged, they get hard, and when the blood pressure arises and they have to push through these small arteries, now they rupture, stroke. Finished. All right. Or worse, part of this fat get loose, right? It goes into the vessels of your heart, and part of your heart dies, boom, ruptures, and you die. Or this clog goes to your lungs and pushes again, plugs one of the arteries that have to supply oxygen to your tissues, and you're breathing, but you die because there is no oxygen going to you. You see? So how much important is it to be flexible? your blood vessels. And this flexibility is created by God with these two proteins. Mainly, there is other, but I'm not going to talk. And they must be flexible. That's the problem. Now, if you calculate now all possible options of these 20 amino acids that can combine to make one protein, 100 amino acids combined. All right. You'll get what number? Let's check it out. Now, let's take two dices. Two dices. Each dice is a cube with 6 sides. These 6 sides got the different numbers. 1, 2, 3, 4, 5, 6. So you've got two dices. How many possibilities you've got with these two dices? Very simple. 6 sides, 2 dices. 6 by the power of 2 is 36. What about 3 dices? It's going to be 6 by 6 by 6. So it's going to be 6 by 30 is 180, 6 by 6, 36, 216. Right. Now if you've got 6, it's getting more than 40,000. That's a 6 dices. I've got 20 amino acids that need to comprise 100 to make one protein. One protein. Now, guess what the number it is? Guess. You won't even imagine how much it is. Now, how can we calculate this number? Take your scientific calculator and punch there 20 on the power of 100, and you're going to see what's the number. It's a 1.2 by 10 on the power of 130. That means you write the number 12, and after the 12 you put 129 zeros. Now, that number, just I want you to think about for a moment that number. This galaxy behind my back, Milky Way galaxy, our galaxy. Our Milky Way galaxy has 200 billion stars. It means 2 by 10 on the power of 11. 200 billion stars. That's our galaxy. And that's 11. Where is 130? Where is 11? Right? The power here is 11, the other power is 130. Now, if you think about your life, how many seconds you think you've got? Say, average life of 70 years. It's a 200 million seconds. 2.2 billion seconds. Or 2 billion and 200 million seconds. So, if you're 32, you already passed in your second billion. Second time. Right. So, that's billion. A number with 9 zeros. Right. This number, the combination, the possible combination of the amino acids are 1.2 by 10 on the power of 130. Now, that number, if you think it's easy and well, try to write it down. It will take you more than 2 minutes if you have to write a 0 every second. Now, we said the numbers of the star in our galaxy is 2 by the 10 on the 11th power. Now, let's check up how many stars you've got in a whole universe, and these stars are comprised of atoms. So, only in our galaxy, the number of atoms are 10 on the 68th power. Now, all the atoms in the visible universe, we don't know what's invisible because we can't detect it, but all the atoms in the visible universe are 10 on the power of 82. And now you can start getting clever and says, no, well, it's not so much, man. You just put the stars of our galaxy, 10 on the 68, amplified by 2, multiplied by 2, and then you've got 10 by 30. Wrong. Wrong. You can't amplify, multiply 10 by 68 power to reach 10 by 108. You need to put another 62 zeros after it. So it's not double. You need to so many zeros after it, and that's by 10, 10, 10, 10, 10, 10, 10, not by 2. Right? So that's very important. So that huge number that I gave you, 1.2 by 10 to the power 130, is the possible combinations of the amino acids that to get connected to make one protein, which builds one structure in your body, which builds another structure and so many structures. It is just incredible. How can this can work out without any hiccups, without any trouble? Well, the hiccups when it comes, it's called either death or sickness, but that's a different topic. But the question is that we still got 7 billion people walking on this earth with all of this process coming without even thinking about it. You see what we're talking about? So, very important thing to realize. You need to be regenerated in order to exist. Because your cells are dying and they need to be replaced by the new one. The cells are made with different structures. The structures are made of different proteins, and these proteins are made with, as I said, with amino acids, building blocks.
But let me show. This is the cell. You can see a 10,000 times magnification, electronic microscope. This is the nucleus where is residing your DNA. This is where your genes are that determine what's going to be you. Exactly your personality. This is how the genes get transcripted. This is 1 million time magnification. That's the your DNA. Each cell of your body, each cell has 1.8 meters of your DNA. Can you imagine? Each cell. And you've got 10 trillion cells. And this is now how your DNA is going to get composed. It's organized. There is it, the helix. Huge protein, huge. You can see with incredible structure. That's the biggest molecule. It takes so much and carries so much information about you. All right, let's go again back to the cell. Now again we're watching the cell. You're going to see the cell replicating. You see it's dividing everything by 2 from one cell. It is going to make a wall between them, and it's going to be 2 completely new different cells. Right. Your DNA, this is how it's read here. It is again recreated. It's a lot of molecular machines that are reading your DNA and copying it. It's very interesting that your DNA is consisting of combination of only 4 amino acids, and this combination of 4 amino acids actually recreates all your personality. And this is actually a real-time speed, and this is the single strand, and there is the genetic code made by these 4 amino acids. Right. And there is a base pair, and this contains all original
So now what's happening is that if they are not regenerated properly, you see that huge number that I gave you, it must be one of these options must happen, not 1.2 by 10 of 130 power. One of these options only must happen. Otherwise, I'll wake up in the morning and my skin is going to be blue. Or I'm going to have 3 arms, or 3 eyes, or 4 ears, etc. You understand what I'm saying? They must be regenerated again in a way that they can replicate you properly. Otherwise, it's finished. You're not going to be the same person. And mistakes can happen, and when this happens in the genetic level in your DNA, then it's called cancer. You know? So the mistakes are paid terrible. But the life carries on. So all of this process must be regenerated. It must be regenerated in such a small ratio. So this is a miracle. You understand? I would like you to comprehend it. How amazing is it? Such incredible events are happening in your body without even thinking of this. With so many possibilities of the protein synthesis, right? It is just incredibly amazing how this can happen regularly. Now, to give you an example, the skin cells, especially the cells of epidermis, they replace daily. This is why you've got dust in your room. And it's good to clean the dust regularly because actually you're breathing your dead cells or the dead cells of your guests or the dead cells of your dog and the cat. Not nice, right? So your epidermis cells are replaced daily. Your fat cells are replaced slowly every 10 years. The same with your body bones, but the bones are regenerated continuously. Just your full skeleton is regenerated every 10 years. Now, when you look at this, the generation and the regeneration of your body and your tissues and everything else must be done daily. You know? Now, you can't just say, oh, well, that's a dice, that's happening by chance. By chance, even to throw 2 dices, it's 1 out of 36 possibilities. Just 2 dices. And we've got here 20 amino acids, which you have to fill 100 different places. With different ways, on the same way that it was the previous one, so that you're not going to lose the color of your eyes, not your voice, not the length of your nose. You know, can be short, can be long. The color of your skin, the color of your hair, etc. Now, we can't just ignore this and say, well, chance. Chance doesn't happen. Such a chance in regeneration is not going to happen. So that's a miracle that God creates in you every day. I don't say that He virtually makes the effort to put the amino acids together, but He creates a system that can maintain that, and He maintains you every day. So that's it. So I'll finish this lecture with the words of the psalmist, which we read in Psalm 139, verse 14. I will praise Thee, for I am fearfully and wonderfully made. Marvelous are Your works, and my soul knoweth right well. These words are written 3,000 years ago. But they clearly shows us there's no dice in the life. There is a God's care, and there is a marvelous and unique way that God maintains life. May God bless you. Thank you very much for your attention.